Okay, I hope it's working. So hello everyone. In this video I'm planning to respond to some of the Sabine Hossenfelder continuing critique of high energy physics. I would like to start with this video. I was asked to keep this confidential. This video is actually very good, and I agree with its main idea overall, and I will talk about it separately in a different episode. But I would like to separate the political questions from scientific ones. So in this video I'll be only addressing scientific ones. So I will only look at small piece.
And has anyone even noticed that the US government spent another $2 billion or so on a new particle collider at Brookhaven? Its purpose is to improve measurements of the quark and gluon distribution inside of heavy ions. What's it good for? You're not supposed to ask. You're supposed to believe that you're too stupid to understand what it's good for. But let me fill you in. It's good for keeping particle physicists employed. Meanwhile, the Chinese are laughing their asses off that you think it makes your country worth defending. That particle physicists have created these bubbles of useless research is not a problem that can be fixed from inside the community. The only way to fix the problem is to stop paying them. I'm afraid that this is exactly what's going to happen.
Yeah, well, actually, the funny part I quite agree about, as I said, but today let me talk about the scientific part. So I decided to start with the collider question because that's literally built next to me, right? I'm in Stony Brook right now, so BNL is more or less right across the road, and I happen to hear the presentation of a person in charge of this project about why, what it's needed for. Let me, I guess, share my notes. So yeah, basically you can ask why do you even need it if you already have something like LHC, right? So the analogy which they gave is like with studying the interior watermelon, right? If we have a watermelon, we want to know what's inside of it. One way to do it is to smash it across the wall, right? And it will break it into small pieces, and we'll learn that it's made out of pulp, this red part, and some seeds. But that will not give us any more detailed information about how exactly seeds and pulp are packed inside. If we want to know it, we need like other tools, like for example a knife to cut a slice of watermelon out. Sorry, and to see how accurately seeds there. Basically, in this analogy, watermelon is like proton, and smacking in across the wall is like what we do in LHC. In LHC, actually, we're smashing a pair of protons, or proton or antiproton. So this means studying very high energies, right? And we know actually how proton, how quarks inside proton behaves at very high energy, right? We know that proton is made out of 3 quarks, right? 2 up and 1 down. And we know that if you measure their behavior at very high energies, which means small distances, they are pretty much asymptotically free. This means you kinda if you just go really close to proton, starts trying to drag quark inside of it a little bit, it doesn't react very much. It doesn't care, right? Whereas if you try to drag it out of the proton at a really large distance, I raised the proton accidentally, like this. You will realize that it's actually very strongly coupled to other quarks, and you can't drag it out. At some point, what will happen is that the energy which you pump into it will create a quark-antiquark pair, such that the quark which you're dragging out will be paired with antiquark and form a meson. And the proton remain intact. Basically, the second quark in this quark-antiquark pair will stay in the proton instead of this one, the one which you dragged out. So basically, you could never drag single quark out. This is called confinement. And this is pretty much the most interesting phenomena in particle physics. So it happens at large distances and small energies. I mean, relatively small, right? That's where our perturbation theory, which is our main and only tool of studying high-energy physics, more or less, outside of other tricks which I talk about, fails. We don't really know how to understand this regime. So I think it's very interesting to get some experimental data about it. In fact, I have a friend who is working in BNL right now, who is specifically studying QCD, and he's very excited about this collider. And I'm curious myself. This confinement problem, it points to probably some fundamental issue which we have with our formalism, with quantum field theory. It might reveal that it's actually deeply flawed, and I'm really glad that we have a chance to see it on relatively low energies, so we don't have to go to some sort of all the way to quantum gravity and Planck scales to see it. In fact, that there is a reason why defining Young-Mills mathematically is a millennium problem, because it's not strictly speaking mathematically defined. Perturbation theory doesn't give a rigorous mathematical definition of this type of theory describing this phenomena. Well, I mean, I think I'm not gonna comment more on the detector side, because I don't know that much about it because I'm not an experimental physicist. So I'll switch more to the theory side. Here, Sabine wrote a book. It's called Lost in Mass. I should admit immediately that I haven't read the book, not out of disrespect, just I didn't have time yet, and I have troubles now reading books, even the one which I really would like to read. So basically, overall I know what this book is about because I know what human ideas is. She basically complains that people are producing this kind of useless mathematical formalisms which don't really lead to anything, and they're disconnected from experiment. This is to some extent fair. However, I would like to point out that we do not always live in a situation of a scientific revolution, and in the intervals between two scientific revolutions, we basically need time to develop new formalism. Think about, for example, Einstein and Einstein general relativity equations. They are written in terms of Ricci curvature and scalar curvature. These are notions which were invented by differential geometers. You wouldn't be able to write down this equation without them, or at least you would have really difficult time finding them independently. Basically, my point is it wouldn't be general relativity without differential geometry. And people were developing differential geometry without motivation for space-time, of course. Nobody could ever guess that space-time has something to do with it. They were probably just playing with simple shapes like spheres, and if you ask them, hey, why do you need this? He's like, oh, look, it's just the sphere, it has some curvature, and like, and the plane doesn't have it, or even cylinder doesn't actually have it, right? And you could say, well, why do we need this? It's just not, it doesn't really help for any real physics, or the help is minuscule. And nowadays, general relativity is used even to correct GPS readings, right? So basically it's kind of ubiquitous. The main point, I guess, that she thinks that mathematical beauty, which drives those people, is something subjective and unreliable, right? Some people consider this beautiful, these things to be beautiful, other people consider other things to be beautiful, and so on. But math is somewhat special. In math, mathematical beauty is in some sense objective. It's equivalent to conceptual simplicity. And conceptual simplicity means effectiveness. It means it frees up your times for more important things. Like, for example, if you only know one example of vector space, right? You would be able to work with this particular case. In another case, in another situation, when you see in vector spaces, you have to learn some specific things about this particular case again. But if you're really skillful with vector space in general, as an abstract concept, all those questions will look the same for you. You'll realize that, oh, okay, this simple errors on the plane. They're actually similar to some functions on the line. I could use the same intuitions in both cases, and that saves up my time. And by itself, by the way, it also has applications even in the real world. Say, a lot of people have to study a lot of analysis or algebra just for the industry, just because they're engineers or, I don't know, economists and so on. And because they're driven by the immediate necessity, right? They learn things only as deep as needed for the particular task. And in some situation, they could struggle with certain questions, right? And basically, if you think about it, our knowledge, the boundary of our knowledge of every human, right? It's not really just smooth line, right? You learn something in a non-trivial way. It has this, fjords and islands. You learn something here, but now you have a gap, or you have an island of knowledge here. It's not very well connected to the rest of your knowledge yet. Something like this. If you're dealing with a professional mathematician, his knowledge extends beyond this point, right? He has his own frozen island somewhere, but this part of his knowledge is totally robust and sound. Because he learned more abstract concepts, it allowed him to understand simple applied things better than those people who only care about applied things. And he has a chance to explain them much more effective, much better. There is an example which I want to show you. You know how Maxwell's equations originally look like. Guess I have to stop sharing this screen, start sharing this one. Yeah, this is Maxwell original paper. Well, I don't know actually. Maybe it's some sort of translation, or I don't, or like I don't know actually which language he was writing in. Yeah, James Clerk, I guess. It's probably original. Let me find the headline. Dynamical theory of electromagnetic field. James Clerk Maxwell. Published in 1865. So yeah, found the equations for you. Here's basically three equations here, and these equations here, right? He has like metric equations in this paper as well. So of course, in total, he has more. He has currents. He has E, D, H, and B. Like the all standard vectors here in principle, but his notations are quite awful. So nowadays, we could write down them way simpler, right? They just will be written in one line. The Hofstadter times differential times Hofstadter again times dA equals current, for current. A is a four-dimensional vector potential, so everything is like manifestly Lorentz invariant. And it's actually, by the way, only 2 equations out of standard 4. Other 2 are actually trivial. Like if you introduce a notation f equals dA, so that this equation is basically star d star f equals j. The second equation is just df equals 0. But it's not a real equation, it's just the fact that d square equals 0. It's the fact that the Ram differential squares to 0. It's just a general fact of differential geometry. That's what differential geometry allows you to do. It allows you to separate trivial things from non-trivial things and frees up your time to think only about non-trivial things. We invented already enough things. We kind of discovered a lot. Of course, we want to discover more, but now we also need to focus about like the structure of our knowledge, how to structure it better. And this is not easy, but my point is we would like to do what we did with Maxwell equations with all of our theories, like quantum field theory and string theory. In some sense, our attempt to mathematically define them properly, basically solving this millennium problem, is a guidance for our human math. It's a constant challenge, but it's quite rewarding in the sense that in the cases where we were able to define certain subsectors of string theory or some quantum field theory mathematically rigorously, it enriches our mathematical knowledge enormously. So my point is quantum field theory and string theory, it helps us with abstract math. We wouldn't really have things like Gromov-Witten invariants of maps of curves into Calabi-Yaos, right, and all the beautiful theory of these invariants without topological strings, without Witten's paper. We wouldn't have Donaldson invariants, most likely, or didn't have such a rich theory of them without supersymmetric Young-Mills. And we wouldn't have probably even such a perfect understanding of geometric Lagrange as we have today. And I'm not sure whether we would still have a proof which was recently given. I don't know, I haven't studied it yet. But we wouldn't have such an intuition. We didn't have super Young-Mills, basically. We also wouldn't have the not polynomial invariants without Witten's paper, without Chern-Simons functional. So in all these cases, physical intuition provides some additional knowledge, additional insight, additional point of view, which is missing from math itself. For example, homological mirror symmetry, which is the duality between category of coherent sheaves, derived category of coherent sheaves on some Calabi-Yau and Fukai category on a dual Calabi-Yau, is basically explained by T-duality in string theory. The geometric Lagrange, which I mentioned, is explained by S-duality in n equals to 4 super Young-Mills. And relation between Donaldson-Witten and Zerberg-Witten theories are explained by Higgs mechanism. The basically mathematicians wouldn't be able to have such intuitions on their own. And these invariants, they describe four-dimensional manifolds. That's what mathematicians would like to study. They would like to have the classifications of them or invariants of them. So I think my first point is that high energy physics in its current form, if you call it that, at least helps the development of human mass. Of course, I understand that the counter argument could be, why do we need this mass? Like, is this mass needed for anything? Like, we don't know whether it will be useful at any point in the future. Well, it's true. You don't really know whether the certain formalism is useful until you cash in, right? Until at some point you get some sort of general relativity moment, right? When it turned out, oh wait, actually, all this differential geometry which you're building, it was needed for something, right? So because of that, I decided to prepare certain examples of cases where all those abstract quasi-mathematical theories already actually led to some fruitful result in some real-world physics, which we could, in principle, measure in real experiments. They're kind of scarce, I agree, but it's not like they're not existing. For example, that's one of my favorites. If you just study a simple model of electrons on two-dimensional lattice, two-dimensional material, think about some sort of graphene, but on a square lattice. The electrons hopping from one side to another. The translation operator I call in the x direction, we will call tx. In the y direction, we will call ty. Basically, these operators would commute if we didn't imply, usually commute, of course, but if we also had a flux of magnetic field perpendicular to the xy plane here, then they stop commuting, because magnetic flux through a circle affects the phase of the wave function of a particle which went around the circle, right? So if basically our electron jumps around circle, around the square plaquette like this, so it jumps like ty inverse, tx inverse, tx, right? I apply these operators in a sequence like this: 1, 2, 3, 4. It should be equal to the phase induced by the magnetic flux. This is magnetic flux through the plaquette. And the Hamiltonian, the standard hopping Hamiltonian of this model looks like this. Plus some constant. Yeah, and this simple Hamiltonian is known as Hamiltonian of a two-particle relativistic tonal lattice, which is a very famous system, and it turned out that have connections to certain quantum geometries. Basically, let me show you the paper. Oh. Yeah, so yeah, here it is in a standard form and in canonical variables. And well, let me try to see whether I could find you where they introduced it in relation to the lattice. No, okay. Well, I don't know, but it's the same Hamiltonian. So basically, it is described by the partition function of 5-dimensional supersymmetric Young Mills in the omega background, which is equivalently partition function of refined topological strings or some special Calabi-Yau manifold they call local P1 cross P1. Or the third way to think about it in terms of representation theory, it's some correlation function of intertwiners of some representation in quantum toroidal algebra. So there's all sorts of beautiful math related to the simple model of two-dimensional electrons. And in fact, they use this math to solve it, to find a spectrum. And the spectrum is looks really amazing. Yeah, it's really beautiful. How the allowed energy zones look like as function of flux. That's called Hofstadter butterfly. Basically, they have some sort of fractal behavior. Yeah, here's the expanding of this quantum periods. Yeah, different versions of this butterfly. Well, you could say, okay, this is some sort of non-interesting, maybe two-dimensional material, yeah, but actually people kind of like them. I mean, for example, there's another famous example like this with fractional quantum Hall effect, right? People were interested in fractional quantum Hall effect, and it even has some applications in terms of fine structure measurements and so on. It really was important. At least there was excitement about it for a while, and still is. And there things like Chern-Simons functional plays an important role. And this was discovered by mathematicians, right? They were just studying connection and some sort of differential cohomology theory. I don't know for sure. Jim Simons, they were literally working here. Jim Simons was the head of the math department in Stony Brook, where I am right now. Well, another example to talk about is probably conformal bootstrap. It's all originated from two-dimensional conformal field theories because they are used to study strings, right? That's two-dimensional conformal field theory is a theory on a string Worldsheet. I don't want to talk right now in great details what conformal field theory means, but in the real world it describes critical phases of matter at the moment of second-order phase transitions. Basically, water at its critical point and ferromagnetic at next to its Curie point are described by the same conformal field theory, which is called three-dimensional Ising. And now these two-dimensional techniques developed for string theory purposes has been extended to higher dimensions to cover already these physical examples. It involves sort of numerics. So basically, it's some numerical tricks. So I don't know it very well, but it allows you to make actual predictions for critical exponents, which things measured in real life. It's basically how heat capacity, correlation lengths, behaves as a function of temperature next to the critical point. So it's really quite inspiring. I mean, it's not really decoupled from reality, but none of this would be possible without our background in conformal field theories, which mostly came from studying string theory at some point. Yeah, so, and recently there was even further developments. So people come up with even better ways to find again the spectrum of Ising model. Or like basically, yeah, the also studying of Ising model and other CFTs using what's called phase sphere regularization. This phase sphere is basically an example of non-commutative geometry. In substance, you could say, well, it's kind of not that hard, but just our overall knowledge and appreciation to the subject of non-commutative geometry allowed it to be so popular that even pretty applied physicists start using it, right? So I think this is also worth mentioning. Another example could be this amplitude discovery, which I decided to talk about predominantly because Sabine has actually mentioned this example in one of her videos. And she was somewhat skeptical, and I also don't want to like exaggerate this achievement or downplay it. Neither exaggerate, neither downplay it, right? But I would like to point out that it also was originally discovered in n equals to 4 super young mills. So it's not just some super young mills, it's maximally supersymmetric young mills. And that's where it really shines. And only then people start to wait, where it was? Start to develop some sort of techniques and ideas how to go beyond the supersymmetric case. This is called Associahedron. This is basically a way of writing down huge sum of Feynman diagrams in a more simple, in a more effective form, in a simpler form, as an integral of a certain polytopes. I don't know whether it's anyhow fundamental, whether it means anything yet, but at least I guess it simplifies calculations, and that might be helpful in some situations, because for calculations which you need for actual colliders, the sum of terms is just enormous, and it's really difficult to do them. And if you remember the story about the mass discrepancy in W plus boson, well, that might be just coming from the fact that somebody just made a mistake in the calculation, or maybe like it wasn't even clear. I mean, the uncertainty intervals are really big there. So making perturbation theory effective, right, computable, is a meaningful desire, meaningful endeavor. Yeah, but I unfortunately don't know that much about it. Yeah, one of the most beautiful examples probably would be holographic duality. Yeah, I don't know whether I have a paper about it here. Yes, though it came from well, okay, the idea existed even before, but the paper which is most famous here is the Juan Maldaceno's result. That was again achieved in 2B string theory, or maybe I should say again n equals to 4 super young mills, the same main hero maximum supersymmetric young wheels in the original framing of ADS-CFT correspondence. And then later people realized, okay, maybe supersymmetry wasn't really essential here. Could we break it just and get some non-supersymmetric model? And that's what people here did, right? It's a Witten-Sakai-Sugimoto model of quantum chromodynamics. In some sense, you could say it's kind of wrong, right? That the meson spectra which they got, it just doesn't add up. It just doesn't correspond to correct answer. It's off by like 20% or something. But we could still think about it as some sort of toy model. It still gives us some idea about how a dual geometry to confinement might actually look like. And in general, yeah, that's a big question. What attitude should we have towards toy models like this one? That's certainly not how an actual universe works. Or like in general, or like things like Zimberg-Witten solutions, which is also again some supersymmetric young wheels, but it's a model of confinement. It might give us some idea how things could work in non-supersymmetric cases, or in this case, again, there is no supersymmetry here. It was already broken, but maybe it will give some clue how to, build on this, right? How to improve the geometry to get confinement right. Of course, I couldn't say anything for sure. I couldn't guarantee you anything. And this is not the only application of holographic duality, right? This holographic duality, as you probably know, it's all over the place. People recently was using some sort of techniques like this, trying to explain black hole information paradox. I don't know. They have they're basically somewhat successful, but of course, again, we couldn't really measure anything because it's some sort of quantum gravity, right? We're dealing with black holes. We can't even measure Hawking radiation, so we couldn't really confirm it. And again, I haven't studied this topic very well, so don't want to lie here. But there's definitely something beautiful about holography. And you could say, okay, it's very suspiciously, it only works in some sort of anti-de Sitter geometry, which is like as far from our actual universe as possible, right? It's basically like you need to take some sign there and make it opposite, right? Which is like, it's different by sign, right? It's like, well, it's something wrong. And of course, people had all these attempts about analytic continuation of result from ADS to DS. They didn't quite work. But instead, we have some form of celestial holography. It's basically correspondence between, again, observables in four-dimensional space with observables on the celestial sphere, right? That's the infinitely far away sphere to which the light rays will point. And you could say, well, it's not actual holography, it's something else. It's more like a 4D to D correspondence. Yeah, it's fair, which more looks like some sort of AGT, right? Aldaga-Techkova correspondence, which also came from supersymmetry originally. But again, I don't know whether we could ever push it further than that. And finally, I want to show you the paper where it was. Yeah, the new paper. This one is about something very real. It's a relatively new phenomena. People notice that if you have, graphene, right, this two-dimensional material, and you put another layer of graphene on it, and you twist one layer with respect to another at certain angles, you'll be able to see superconductivity in this material. and these angles are called magical angles, and it's a interesting problem to explain, and it's something which could be seen on actual experiments, right? And this paper tries to explain it, and it uses gauge theories, basically study of G bundles, right? Or should I say vector bundles. And you could argue, well, this paper doesn't have supersymmetry at all, right? Everything here is non-supersymmetric. Yeah, but the intuition here is intuition about stable bundles, and it kind of came, I would say, from fruitful communication between mathematicians and physicists in the study of supersymmetric gauge theories and their relation to some complicated moduli spaces where we actually need the stability conditions, where we actually care about which bundles are stable or which bundle are not, and because we care about singularities and whether you'll be able to calculate some integrals over this moduli spaces. So I understand I probably haven't convinced you with give you some sort of pretty bad examples and really limited. So it might look really pathetic, but I don't know how to make a better point. I would say the influence of all this study of mass and quasi-mass topics is more like subtle, right? It's it build you formalism and it gives you some intuition, and then we could push this intuition further, or we could structure our knowledge better. And yes, I agree that right now we haven't even provided any scientific revolution for society. Well, unfortunately, I don't really have any good ideas how to achieve that. But I personally don't know what to do. Like, should we abandon science because of that? It's just we're living through quite harsh times. And I agree that this pathological structure of academia, which Sabine is talking about, is a valid point. It certainly probably might be part of the problem, and I certainly would like to talk more about it. So I will make a separate video about this topic. However, in terms of funding, I would like to show that Sabine's criticism is a little bit hypocritical or one-sided, right? Because if I look at the total fundings, yeah, where it was, this is for NSF, right? What do we have here? For LIGO, for example, $40 million, right? Request for year 2025. It's from NSF. For Large Hadron Collider, it's upgrade to it, 20 million. For IceCube Neutrino Observatory, it's where congressional whistleblower already said we have a directed energy weapon and like a intergalactic control tower, right? Well, for reasonable price, just what is $4 billion per year. Of course, it's only NSF grant. In fact, yeah, I found you the total breakdown of all funding. If you look at congressional website, right? I don't know if I could open it. Yeah, where all funding comes from. So basically, main places which I was able to identify here are NSF, maybe NASA, but doesn't really do high energy physics, I guess. I mean, it's not about string theory, right? And Department of Energy. And that's what found all those colliders. So let me find it here. Yeah, here it is. This is the Department of Energy Science section, funding, high energy physics. So as far as I remember, yeah, they asked like for $1 billion. Yeah, in total per year. So of course, like you could say, well, that's kind of a lot. What should we compare it to? Yeah, for example, I found you the total. Somebody made a review of total funding of science. We see basically what takes the most: life sciences, right? 40 billions. Engineering physics has only 12 billions in total, but again, high energy is just a small fraction of it. At the same time, we see what is this, 4 billion given to psychology. That's like literally where half of the papers are fraudulent. Like, yeah, replicability crisis. Okay, doesn't have any numbers. Replication crisis. Psychology. Yeah. Study replication rates with 23%, 48%, 38%. Half of the studies are just not replicable, which means they just complete fraud. Just complete fraud. And still they're getting $4 billion. You could ask why. Because, well, probably because these are fields which are actually related to policy making, to decision making. Basically, it's some sort of propaganda machine, and I'm planning to talk about it in a separate video. Of course, any coercive funding of anything is immoral, so I'm against all of it. Where is this paper? I'm against all of it. Science should be funded voluntarily, but accusing high energy physicists of wasting money when you have this and this, and I haven't even talked about Department of Education, is just some sort of hypocrisy. Yeah, Department of Education requested $42 billion in discretionary funding in the budget. I skimmed through it. It doesn't even have the word physics in it. I don't know what they're teaching there. Like, what is it doing there? It's what, native Hawaiian education, education of Homo student in use, migrants education, and I'm afraid this 42 billion is even not the full budget. Okay, I think I looked it up before. What's education budget? Yeah, its budget is 200 billion, 260, 270 billion. So it's just unreasonable in the situation to blame some sort of $20 million LHC upgrade or $2 billion BNL collider when you are literally wasting this amount of money on something which doesn't have any reasonable purpose at all. Of course, I am strongly pro cutting all the government funding, but we need to see where the actual waste happens. And I don't know how much would really wasted here. Of course, like on the free market, we would be able to see the true values of this type of research, whether we actually want to have this National High Magnetic Field Laboratory for $40 million, which nobody ever heard about, or we would have more money given to LIGO instead, which everybody is like excited about, right? Which is like on the news because it's like gravitational waves. We like want to know more about them, right? The public would be donating money to this lab. Yeah, I don't really know how to finish this video. I feel like maybe my arguments were not really convincing, and overall Sabine's message is on point, but I just want to really stress out the difference between the political message about cutting the government spending, which again is collected through coercion, versus whether actually we need abstract mass, supersymmetry, quantum field theory, and things like that. All this new BNL collider. Yeah, I'll talk about more important questions next time. I guess I will end this discussion here. Thanks for watching, or probably I don't think you watched it all because it's so long. I'm not really good at giving such discussions, but that's literally all which I can do. Yeah, thanks for your attention.